Welcome back. It's been a long day, but I can tell you it's warmer outside and it's nice and cool inside. That's one reason to be inside. And the other reason to be inside is that we get a great talk by Professor Thomas Cutsem from DistriNet. He will give you an update on what's happening in blockchain and distributed ledgers.
Thank you so much, Bart. Good morning, everyone. Good morning. Good afternoon. Sorry. So I'm the last speaker of the day, but I hope to still catch your interest with a discussion on blockchain. So as Bart mentioned, I'm a professor here at KU Leuven. I'm from the same group as Professor Frank Piesens, who you met this morning, talked about secure software. And this is sort of also as an introductory lecture that I give as part of our Advanced Master of Cybersecurity. And so we're going to talk about blockchain. And then maybe I should open with why talk about blockchain in 2026? Because nobody's talking about blockchain. Everybody's talking about AI these days, right? So what about blockchain? Well, first of all, it's you're probably aware that digital assets, cryptocurrencies today are a well-established digital asset, right? Companies hold Bitcoin on their balance sheet. Certain governments are buying it, even pension funds are buying it. So it's sort of a legitimate asset class, an established asset class today. There's DeFi or decentralized finance. Anybody heard of DeFi in the room? A few people, okay. So DeFi are protocols, automated protocols that offer banking services like taking out a loan, but without a bank in the middle, sort of disintermediated finance. Stablecoins, anybody heard of stablecoins? Again, a few people, okay. Stablecoins are cryptocurrencies that are pegged one-to-one to a traditional fiat currency like the dollar. And Tether or USD coin are quite popular these days, and they're being used as an actual payment mechanism because, yeah, Bitcoin is not typically used for payments. You typically use it to hoard it, I guess, as an investment asset. But stablecoins are becoming quite popular for payments, in particular international payments. And so it's interesting. We just had a talk by MasterCard on sort of payments using your traditional banking card, and stablecoins are becoming like a more digitally native way of doing payments online. There's RWA or real-world assets, so companies like BlackRock, like massive companies that typically issue a lot of stocks or bonds or ETFs, for instance. These are also all moving on-chain, so being stored and tracked on the blockchain. And finally, a lot of what has made all of this possible in the last years is increasing regulatory clarity. We just had Laura talking about regulation. She didn't mention MiCA and Genius Act, but these are regulations that are basically setting clear rules and guidelines for companies on how to deal with these digital assets, okay? So we have long left the realm of the cypherpunks, even though I will definitely talk a bit more about the origins of where this all came from. And so we'll dive into where did blockchain originate, as of course Bitcoin, and what was the origin story and what was the key thing that why Bitcoin needed to invent something called a blockchain. We'll talk about the cryptographic building blocks of blockchains, how blockchains process transactions, look at the life of a blockchain transaction, talk a little bit about consensus protocols, permissioned and permissionless blockchains. If there's time left, I can talk a bit more about Ethereum, the second largest blockchain of today, and then we'll conclude with some open challenges and recent trends in blockchain. So let's talk about the origins of this technology. So the origins of technology like blockchain have to do with the desire to create a purely electronic version of cash, right? So we all know cash. We don't use it that much anymore, right? Because we tend to use the plastic. But cash is an interesting type of medium to pay someone, because I can hand you a dollar bill, I give it to you, and we have engaged in a transaction that is completely anonymous, right? And we don't need these the issuers of the cards, or we don't need any centralized institutions to clear that payment. I just hand over the bill, you give me the change, and that's it. It's a purely peer-to-peer way of transacting. But online, we don't transact peer-to-peer. And again, this is a perfect follow-up to the talk on by MasterCard, because that has very nicely demonstrated how many parties, how many intermediaries are involved between you holding your plastic card and then inserting into the payment terminal. There's a whole slew of parties behind the scenes that are being contacted to clear that transaction. Okay, but there was this group of cryptographers called the cypherpunks back in the 90s that was very actively engaged with the idea of how can we invent a digital version of cash. So money as a bearer instrument, something you can just hold digitally and transact peer-to-peer online. And actually, even before the 90s, that idea was already tried. So there's DigiCash, that was a company by David Chaum, famous cryptographer, relied on his invention of blind signatures. So the idea of an authority signing something without the authority actually knowing the contents of what is being signed in order to have actually anonymous payments online. So the big problem that electronic cash faces is that, as you all know, something that is purely digital, like a file, right, or some number, it's very easy to clone, right? I can just copy bits, right? And if there's one thing that a money issuer doesn't like, is that people clone their money, right? This is why euros and dollars have all of these sigils on them, because you don't want somebody just putting it in a copying machine and printing the money, right, or duplicating the money. And so this is called the double spending problem. So graphically, let's say that Alice wants to pay Bob, right? And so she's going to create a transaction, and a transaction is nothing more than a statement saying, I hereby transfer my digital coin number, I don't know what, every coin has a serial number. I will transfer that digital coin to Bob, signed Alice, so she signs it with the digital signature. And she transmits that note over a digital network, like the internet, and Bob receives that note, and they can then use that statement to show everybody else, like, hey, this is proof that Alice paid me this coin, that I now own this coin. Now, the problem of double spending is that Alice can take that same digital coin with that same serial number, and she can create another transaction object where she says that I transfer this coin to Carol, and I sign it, send it over the network, and now Carol has this other piece of paper, this other claim that says that she should be entitled to hold and spend that coin. Okay, so we have just cloned our digital currency, right? So that's the double spending problem. And so how can Bob and Carol be sure that there's only one piece of paper that makes a claim to this coin, right? And so the traditional solution to this, the only solution that people came up with before the invention of Bitcoin, was that you needed what's called a clearinghouse. A clearinghouse is a centralized entity in this whole system that will basically track whether this coin with this specific serial number has already been spent. And so when Alice creates that first note and sends it over to the clearinghouse re-record that. When she creates tries to create another payment with the same serial number, then the clearinghouse will reject the second payment because it has already previously seen that other note saying, no, Alice, you already spent this coin to Bob, you can't now spend it again for Carol. And that's the role of the central clearinghouse. Now, the problem with that central party is it creates risk. It creates technical risk, like what if the clearinghouse goes down, right? And I guess you all remember, maybe in recent years it's improved, but 10 years ago during the Christmas holiday shopping, right? It was super annoying when you were in the store and you tried to pay and the payment wouldn't go through because some server somewhere got overloaded, right? So a clearinghouse introduces that kind of availability risk. There's a security risk, like insider attacks. So if somebody inside the clearinghouse is able to, delete that first, tamper with the database, they might actually create double spend transactions. And there's also economic and political risks, right? So the clearinghouse is managed by a company, and that company can be attacked, right? And no better example to illustrate this than what happened with Euroclear in the last months, right? So Euroclear is holding all of these Russian assets, and then there's a lot of political pressure on that clearinghouse to release those assets, right? So that's just one example. And in fact, DigiCash, the company of Chom, went bankrupt in 1998, and when it went bankrupt, all the digital dollars that this company created were worthless. Okay, so that's the problem with centralized clearinghouses. And so, so when Bitcoin came around, so there was this 2009 or late 2008 white paper, and then early 2009, the network went live by Satoshi Nakamoto, of course, a pseudonym. So what was Bitcoin's breakthrough idea? It was this idea that, well, since having a central clearinghouse is such a big risk, why don't we get rid of the central clearinghouse by making everybody in the network responsible for clearing transactions? In other words, we're going to distribute this clearinghouse. It's going to become this big replicated component in the system, and everybody can participate. Everybody can look at all transactions, verify all the transactions, clear all the transactions. Okay, so that's the core idea. That's really the core idea. And the blockchain is really just sort of a technical construction to create this replicated database of these transactions. It's basically a replicated clearinghouse. So going into a little bit more detail, and again, still at a very, very high level, what is a blockchain? It's essentially a chain of blocks. And what are blocks? They're basically just containers for transactions. In the case of Bitcoin, these transactions are payment transactions. Again, in a very cartoonesque way, you can think of any transaction in Bitcoin as like a statement where Alice says that she's transferring a certain amount of coins to Bob. Of course, you won't see names like Alice and Bob on the blockchain. You will see what's called blockchain addresses. They're just long hexadecimal strings of numbers. But essentially, these transactions are like payment transactions. They get sequenced into these blocks. And then every block also contains the hash of the previous block. Okay, so you just take the full contents of this block, you hash it using a cryptographic hash function, and that hash you store in the next block, and that kind of uniquely identifies this block as following this previous block. Why is that important? Because the order of transactions is extremely important, right? Again, think about my scenario of double spending. Everybody has to agree precisely on the order of transactions. If there is ever like confusion about which transaction happened first, think back to my Alice, Bob, and Carol scenario. You can have this scenario where Alice is deliberately trying to create multiple payments, okay? And you want to avoid that. Okay, so let's look a little bit about how cryptography factors into the blockchain. How is cryptography used to secure the blockchain? So here's a sort of a schematic of, I have a number of these parties that are maintaining this blockchain. They're like maintaining that clearinghouse. In blockchain parlance, you will often hear them called validators or miners, okay? And so these miners, they keep track of these pages, and you can think of these pages as blocks, and the blocks contain all of these transactions. And so zooming in, again, in a very cartoonesque way, you can think of a block in Bitcoin as just a series of transactions, okay? Like Alice paying Bob a certain amount of money, etc., etc. Okay. Now, how do we make sure that not everybody can just write statements in this, right? So if I don't know Alice, but I know she has Bitcoin, why can't I just write Alice pays me $100, right? So to prevent against that, we'll make use of public key cryptography. How? Well, Alice or any party that wants to transact using this system can generate a key pair, right, with a public and a private key that are interlinked. And then whenever Alice wants to create a transaction, she will digitally sign that transaction, of course, using her private key, and that generates a unique signature, a signature that is both unique to Alice and the specific details of the transaction. Okay, and then when any of these miners or verifiers, when they receive a block of transactions, they'll actually verify if these transactions are legitimate. And one of the key things they will need to check is that this statement, Alice pays Bob $10, did in fact originate from Alice. Okay, only Alice can spend Alice's money, right? So how do we do that? Well, we invoke a verification procedure, and the verify function takes the public key of Alice as input, which is also, by the way, embedded in these transactions. So we take the public key of Alice, we take the transaction input, and the signature, of course, and then that verify procedure will give us a thumbs up or a thumbs down. Either the signature checks out and it's valid, or the signature doesn't check out and then it makes the whole block invalid. Okay, and then we'll just reject it. We will just not even process those transactions. There's other stuff that these miners need to do. For instance, checking if Alice in fact had $10 on her account to spend. Right, these kind of things. Now, so let's name one of our miners or validators. Let's call him Victor. So Victor is a validator. They're doing all of this hard work, like verifying all of these signatures. Today, that's rather cheap, but back in the day, signature verification at scale was actually quite an expensive operation computationally. And so the question is, well, what does Victor get for doing this lousy job of verifying all of these transactions and making sure that everybody's playing by the rules? And so what Bitcoin did as a kind of interesting trick is that it said, well, Victor, as a reward for actually sort of creating and validating these blocks, will actually gets to write a special transaction in this block. It's called a coin-based transaction. And that transaction actually says that the network collectively pays Victor a small amount of money. Okay, this is called the Coinbase fee, and it's a way of, you're basically generating new money out of nothing and assigning it to this party that has created this block. Okay, so this is the process of mining, and this is how a cryptocurrency like Bitcoin basically comes into existence. Like every block, a certain amount of new cryptocurrency is being created, and Victor can put this in whatever address they want. Okay, so they typically pay themselves. Now, you can think of this block as like a page in a book, and of course, this system is a live system. Transactions just keep on coming in. So you have to extend this, right? And so the blocks are basically just a kind of a batching mechanism to batch together multiple transactions into one big entity to save on processing cost, communication cost, and so on. But so then later the whole thing continues and we'll create a new block. And then of course the question is, you need to give these blocks page numbers, right? You need to know where to fit them in the book. And this is where what I mentioned earlier, the trick of using cryptographic hash functions comes into play. So you just hash the full contents of this block using cryptographic hash function, and you put that hash in the subsequent block. And this is how everybody can verify that this block or this page actually follows this one. Okay, so it's a way of sequencing. And that's why it's called a blockchain, because you're chaining together these blocks. All right. And why do we use these cryptographic hash functions? Well, the cool thing, and this is where we rely on the security provided to us by our cryptographic hash function, is that if anybody would tamper with any data from the past, let's say I want to tamper, Bob wants to tamper and say, Carol didn't pay me $10, she paid me $100. Well, then, of course, the cryptographic hash will change in an unpredictable way. And so the subsequent hash will be invalid. What this basically means is if you go back in history and you start tampering with the data, you're basically creating your own new blockchain. And everybody else will very quickly see that you have some modified piece of data that doesn't correspond to the canonical blockchain that everybody had earlier agreed upon. Okay? So what's the crypto that is being used by networks like Bitcoin and Ethereum? So some common hash functions you will see in these systems are SHA-256 and Keshak or SHA-3. So typically, you basically give arbitrary input, and you always get a 256-bit hash, and you have the nice property that the hash function is collision resistant. So it's infeasible to find two inputs that hash to the same value, even though those inputs most certainly do exist because the output space is much smaller than the input space. The hash function also hides its input. So given just a hash, you can't recompute what was the input to the hash function. And especially for Bitcoin, it's important that the hash is also puzzle friendly. What they mean by that is that you just by making tiny adjustments to the input, the output changes completely unpredictably. Okay, so it's very hard to establish any kind of relation between the input and the output. The second big component that we need is digital signatures. So digital signatures, because remember my cartoon figure with Alice paying Bob and then signed Alice, right? So we need digital signatures. Bitcoin is entirely built on elliptic curve cryptography, more specifically the elliptic curve digital signature algorithm. Interestingly, it uses this curve called SecP256K1, which back in the day was really quite unusual because it is not the NIST-sanctioned P256 curve that was mentioned in the earlier presentation. Apparently because that curve contained some strange seed that nobody could really justify why it was there. So Satoshi, when he decided on ECDSA, on the use of ECDSA, he decided to use this SecP256K1, which has a much more transparent set of parameters. Okay, and so again, your signatures, of course, we want to have the property that valid signatures must verify. Signatures themselves are unforgeable, and every signature is unique to every message. Okay. Notice, by the way, and this is also interesting, blockchains do not use encryption. Oh, sorry, there's a question.
What's the motivation between having a larger public key? Why do they don't have the same length? The public key is 512 bits.
Yes.
The private key is 256.
Yes.
Is there motivation? Is there intention behind?
I don't know, actually. That's a good question. And I'm not, I don't know if there's cryptographers in the room that can chime in, but I don't know specifically why that is the case. What I do know is that actually what blockchains like, among others, Bitcoin do is they also hash the public key to a shorter number, and that number is then typically used as the address. And the reason to do that is to take up less space on the blockchain because the addresses, they get posted to the blockchain. So that is also commonly done. Okay. Yeah. Mm-hmm. Yeah. Yeah. Okay. Well. Yep. Okay. So notice one thing, there is no encryption algorithm being used here. Right? So blockchains don't typically encrypt their transactions because the whole point is for this system to be as transparent as can be, for everybody to see everything, right? For like everybody to verify everything. Okay, I already mentioned hash pointers. The final cryptographic primitive. Have you heard of Merkle trees? Has this been discussed so far? Some people say yes. Okay. So Merkle trees, just again as a refresher, is this construction by Ralph Merkle that he created to create a single efficient commitment for a very large data set. So what you do is you pairwise hash all of the elements, and then you combine the hashes and you hash them pairwise until you have this nice binary tree, and the root hash kind of commits over the full data set. Why is this used in a system like Bitcoin? Well, what they do is typically when they have the list of transactions in a block, they will store the root hash in what is called the block header. So the block header is like a a tiny piece of data that only contains sort of the important metadata of a block. And there are, like one nice way that you can use this is a system called simplified payment verification, where if a client wants to know if a transaction is part of a block, then if they have a root hash, so if they only download the block headers, which contains the root hash, there's an efficient way to verify that a certain transaction is part of the block without having to download the full block content itself. In fact, you only need to download a few of the intermediate hashes that allows you to recompute the path from the data item to the root hash. And so it's sort of a way of more efficiently verifying if your transaction was part of the blockchain without having to download the full blockchain. Okay, so Merkle trees, that's why they're used in Bitcoin, and you will see them used in other blockchains as well. Okay, so that's it for the cryptography being used. Now let's look at sort of the life of a blockchain transaction. How does this processing actually work? So so it goes in stages, and so one way you can think of a blockchain network, in reality, a blockchain network is a large peer-to-peer network. So that means you have a bunch of servers or machines that listen for incoming connections, and any machine can peer with any other machine. There is no big hub and spoke architecture. Okay, so there's no central server that sees everything. Instead, these things use gossip protocols. So every node knows a few other neighbors, and they disseminate information like this. So the clients, they will submit transactions, and I'll denote transactions here as these little squares. So they just bombard this blockchain network concurrently all around the world. Anybody can create a transaction at any time. And what is a transaction kind of depends on the type of blockchain. So in Bitcoin, a transaction would be like send X Bitcoin from this address to this other address. In Ethereum, the transaction actually calls functions. So it's actually a computer, and you can run arbitrary code on it. You have blockchains like Filecoin that are used for file storage. So a transaction could be like, please store this file for me. So it depends, okay? But for now, just think about the Bitcoin payment transactions. That's the easiest. Now, when these transactions, so any of these clients, they contact one of the peers in the network. And that validator, they will use a gossip protocol to disseminate that information. And they will store these transactions in a sort of big unordered set. This set is called a mempool. So it's just, at this point, the transaction hasn't actually been put into one of these pages of the blockchain yet. Okay. Then, at regular intervals, a subset of these nodes, the actual miners or staking validators in Ethereum, they will occasionally look at all of these transactions that have been collected over the last seconds in their mempool, and they will try to create a block. And the block is actually like a sequence of these transactions. So they will pick some subset and they will order them. Okay. Typically, they will try to choose the transactions that pay you the highest fee. So you can leave a fee for the miner, and the higher that fee, the more quickly these miners will take your transactions and try to put them in a block. Okay. And then once a miner has found such a block, and I'll have more to say about that later, then again, they will gossip that block in the rest of the network so that everybody has access to that information. And when any of these other nodes receive such a block, of course, remember Victor the validator, they will actually check all of the signatures, all of the rules to make sure nobody's cheating. Okay. And so what is really important is that all of these, when you create like a new page in the book, in the blockchain book, it could happen that there might be two parties that have created a block at roughly the same time, right? And they both broadcast this new block. This is, block number 15 in the blockchain. And now some of these parties actually see like, 2 page 15s in the book, right? So they see two blocks that should belong in the same position, which is obviously not possible. So they actually have to choose. And it's very important that all of the nodes in the network choose the same block, right? Because otherwise it's quite obvious what will happen. If there is no agreement or consensus among the network, we will get a kind of split or a fork, as it's called, where one group believes that the first block is canonical and these transactions in that block happened, and the other group believes that the second block is valid and that another set of transactions happened. So you get a kind of bifurcation in history, and you want to absolutely avoid that. And then finally, as I mentioned earlier, so tokens, cryptocurrency tokens are very important in these type of networks. Of course, they are the thing that is typically being transacted in these transactions, but they are also used as a fee mechanism. So you can leave some tokens for the miner, for the network, to pay for the processing. And there's also, as I mentioned earlier, validators can earn additional currency, additional tokens by following the rules of the protocol and moving the protocol forward. Okay? Yes?
Like you mentioned regarding the duplicate certificates, like if the certificates are identical to each other, like the request went, is it possible the request went to two processors, like both says that this is fine,
Yeah.
Alice paid for, and it is identical, and then what will be the case in that scenario?
Yeah, so if you would just sort of copy-paste your payment transaction, in a system like Bitcoin, what will happen is that so the second transaction will be declared invalid because it's trying to spend the same coin twice. And of course, it can happen that like there is a certain point in the history of the network where two nodes each will sort of accept this transaction, but then later when they learn that one of these transactions was first included in some block, then it will render the other transaction invalid. And so achieving this consensus actually takes time, and I'll come back to this later. It's a good question. Okay, so who can be a validator? That's an important question in a blockchain network. So there's two types of blockchain networks, broadly speaking. It's a bit more nuanced than that, but generally you have permissionless and permissioned networks. Permissionless networks are like, for instance, Bitcoin or Ethereum. They are open networks where there is no gatekeeper that says whether or not you can join this system. It's like anybody can join. It's just a matter of downloading the software onto your computer and then going, okay? There's also permission networks. Permission networks are closed group networks where somebody needs to give you permission to participate. A very common example of this would be a consortium of banks that uses a blockchain as a kind of shared ledger to clear transactions. And yes, the banks don't fully trust each other, so it makes sense for them to use a blockchain, but they don't want random people to start injecting transactions into their blockchain, right? So that's an example of a permissioned system. So Bitcoin, Ethereum, Filecoin, I already mentioned those. Those are examples of open permissionless networks. And then these are actually not names of actual deployed networks, but more of pieces of technology, open source software that you can download to actually run your own blockchain. So Hyperledger Fabric, Hyperledger Besu, Corda, they're often used by enterprises to set up private blockchains. Okay. All right. So let's actually dive a little bit more into this property of consensus. I mentioned earlier, whenever a block is found, it needs to be distributed in the network. And it's like really important that everybody agrees that what is the next block in the blockchain, that there is no disagreement there, or that we don't have two different blocks at the same position. And so I already mentioned this, but this is a visual. So you have this nice sequencing of blocks. And I mentioned earlier, every block has this hash pointer to the previous block, which is of course unique, right? But it's perfectly possible to find like two blocks with a different set of transactions and then make them link to this previous block. So both of these blocks will contain the same hash to the previous block. And so they're both valid blocks in their own right. But clearly, we don't want to have these forks, right? We want there to be like one single canonical history. And so these forks, you want to kind of eliminate them, right? If we have this is not a very interesting payment system, because we can just sort of fork money all the time. So we need all the network nodes to agree on a single canonical history, which means that we need a rule to choose whenever we end up in a situation like this. First of all, we want to avoid having situations like this. And if we do encounter situations like this, there needs to be a clear rule that all the honest nodes can follow to select one block over the other, okay? So now there's a problem. Consensus is a well-studied problem in computer science. And as early as the 1980s, smart computer scientists have invented clever algorithms to solve consensus. There's just one problem. They solved it in a setting where it was known exactly how many participants there are, and it all involved voting. Right? So you basically organize a vote. You just give every party in the group one vote, and then you run some kind of voting protocol, and whatever block gets the most votes wins, right? But in these open permissionless networks like Bitcoin, it doesn't even make sense to ask the question to organize a vote, because who are the participants? You don't know, and they change all the time, right? We don't have a fixed list of nodes, and even if we would have a fixed list of nodes, how would we even assign voting rights? So what would we do? Would we just say one IP address, one vote? There's an obvious problem with that, right? Which is that IP addresses are not a scarce resource. I can get as many IP addresses as I want. Well, up to some limit, there is some scarcity, but IP addresses are cheap to create. If you would say, let's use a key pair, let's use your public key as your identity, well, very obviously key pairs are extremely cheap to create. So that's not a good resource to use to assign voting rights, okay? So this is known as a Sybil attack. Sybil attack is where one party can create many, many identities which appear to be independent to the outside world, but they're like, you know, a puppet master that is controlling all the fake identities, like with a botnet. And so that's why we can't really rely on these voting-based protocols. It's simply not possible because they can't withstand Sybil attacks. So there's another thing you can do. You can try to organize a lottery. So you organize a lottery where every node can somehow buy tickets, and whoever can prove that they have the lucky ticket to everybody else sort of wins the lottery and can propose the next block. You have a question? Yeah, so the question is, if you would assign like voting rights or voting order, basically you're destroying the permissionless nature of the protocol, because whoever has a higher voting right can influence the next block in the blockchain. So for Bitcoin, that's problematic because, of course, everybody wants to be the party that creates the next block because they earn the fee. Right? That's a very clear incentive for everybody to want to produce the next block. But there's also a censorship issue, right? So if there is one party that has a higher chance of proposing the next block, they might deliberately censor your transactions, keep them out of the blockchain. That's a kind of a denial of service attack. So there's both wanting to propose the block because you earned a fee, or the more destructive argument where you want to censor some other party. But yeah, very good question. Okay, so the technique that Bitcoin uses is to try to organize a lottery. And what we want out of this lottery is 3 principles. We want the lottery to be fair, proportional, and verifiable. Fair means, in principle, we would like everybody to be able to buy a ticket, right? If you have the national lottery, you should just go into any shop and buy a ticket, and hopefully you don't need KYC for buying a lottery ticket. I don't know if that's still the case today, but that's fairness. Proportionality, also easy to understand. It means that if I buy 10 tickets, then somehow I should have 10 times more chances of winning the lottery, right? This is why many people pool together, right, to have more chances to winning the lottery. And finally, verifiable. If I have the winning ticket, I should be able to, show this to some party, and it should be unequivocally clear that I actually won the lottery, right? So in the case of real lotteries, we do this by on national TV broadcasting what were the winning numbers on a particular day, right? Now, how does this work in blockchain then? Well, essentially, what we need is a digitally scarce resource. That's the key to this whole thing. So what Bitcoin chose as its digitally scarce resource is it chose compute power, which basically translates into electricity if you think about it. So raw compute power, I'll say a bit more about it, but it's basically trying to compute as many hashes as you can per second. And if you have the winning hash, then you win. This is called proof of work, right? So you vote with compute power. And there's also proof of stake, which actually only came later, which is the idea that once you have this idea of digital money or cryptocurrency, then you can also basically say, well, the more cryptocurrency I have, maybe the more stake I have in the system and the more voting rights I should have. So one way you can think about a blockchain network is that voting power is not equal. So for instance, this party here, I show it has like 5 blocks, right? And again, for Bitcoin, think compute power. For Ethereum, think the amount of money they stake. And so every party will have like a stake in the system proportional to that resource, and that influences their voting power, essentially. Okay? That's a conceptual way to think about how proof of work or proof of stake works. And so here's the kicker, right? What blockchain networks guarantee is that as long as a majority of the network weighted by the scarce resource is acting honestly, the integrity of the network is secured, right? So as long as, let's say, if the green blocks here are the good guys, the honest guys, meaning they just follow the protocol as published, while the red ones are potentially attackers that want to deviate from the protocol, as long as the resources of the green guys outnumber the ones of the red guys, then you can create this model that shows that the green parties will be able to create more blocks and will keep the chain honest. Okay. If you violate that property, this is called the 51% attack. 51% attack is where you attack a blockchain by controlling so many resources that you outvote all the good guys. Okay, and I don't think it has happened to Bitcoin, but it has certainly happened to smaller cryptocurrencies. So these attacks are real. And what it shows is that the security of a blockchain is only as good as its level of decentralization of the scarce resource. The more diluted the scarce resource is, the more secure the blockchain, because the harder it becomes for one attacker or one party to amass the majority of the resources. Okay. Yes, indeed. So for Bitcoin, it's hash power, and it typically involves buying these days dedicated ASIC chips that do nothing better than doing SHA-256 hashes. Yeah. How you identify them? So, okay, that's a good question, and in fact, it's sort of here on the slide as well. So how would you be able to recognize an attack, right? So interestingly, and this is important, even if the red guys, the attackers, get the majority, what they cannot do is spend my cryptocurrency, because they don't have my private key. So they cannot generate valid transactions that are signed by my private key, right? So they can't steal my money. That's a good thing, right? What they can do, however, and this is the key attack, is they can do a double spend attack as follows. They have certain cryptocurrency, they make a payment to a merchant, right? They wait until that transaction is included in the block. The merchant looks at the blockchain and says, okay, the transaction is in the blockchain, it's a valid transaction, I will send you the goods, right? I will ship your whatever thing you ordered. Then they go back in history and they create a fork, and then they produce blocks faster than everybody else. And okay, I haven't talked about this, but in Bitcoin, the longest chain is considered the canonical chain. So the moment that you overtake, you go back in history, you fork, and you create a new chain. The moment that you overtake the old chain, all of the transactions in the old chain are all of a sudden undone, right? And so basically you've spent money, you've gotten goods, and now you can spend that money again. So that's a double spending attack that you can only do if you control 51% of the resources. The other thing you can do is you can censor, right? So if I'm an attacker and I control the block production or most of the block production, and I don't like you, then I can just say if I see transactions coming from this address, I'm never going to include them. So the attacks are indeed quite subtle, right? It's about controlling the order of spending, rewriting history, and maybe not including certain transactions. But these are very devastating attacks, right? Yes. Yeah. Well, you can do analysis, right? Like, for instance, if you notice that from certain accounts, money is being spent, and then the history gets reverted, and that money is then, of those specific transactions are all of a sudden erased from history, that gives you an indication that this particular party tried to double spend. Now, what you will see is certain accounts in the blockchain. The problem is that accounts in the blockchain cannot easily be linked to like real world identities, right? Because for me to use Bitcoin, I generate a public-private key pair and I start creating transactions, right? So I can be completely anonymous. Now, in reality, of course, most people will start to use exchanges like Coinbase because they want to actually trade the crypto for real-world dollars or something else. And that's the point where you can actually start identifying who is behind a certain address. And you can be absolutely sure that the FBI knows this and any other government agency knows this. And actually a lot of criminals that have used cryptocurrency in the early days were caught because it was extremely traceable. But coming back to your question, it's a good question. These kinds of attacks, they may not always be very easy. It may not be easy to observe who is behind them, but it is actually very easy to observe that the attack is going on, because obviously, like if you're an honest node and you see these blocks appearing and all of a sudden we go back in history and there's like new blocks being created that are forked, then you notice that you know that there is a double spending attack going on. So the attack itself is easy to observe. Who is behind it? Not that easy. Okay. So, another question, yes. Correct. It is, but in Bitcoin, for instance, the longest chain is the chain that has the most proof of work invested in it. Because in order to create a new block in the chain, you need to actually expend the effort to produce the block, right? Yeah. Yeah. So you're talking about the difficulty, like okay, indeed. So and actually I need to look up, I don't know the precise rule, right? Yeah, indeed. In general, it will be, the longest chain is typically the one that has the most proof of work invested in it. Okay. And I'll talk a bit more about this if I get to it, but we'll see. So this proof of work consensus, actually, one way what Bitcoin is trying to do is I mentioned earlier, we want to avoid a situation where we have these forks. And actually, forks are not always malicious, right? Because in Bitcoin, what happens is all these miners, they will concurrently, each independently look at their mempool, assemble a block, and then they're going to start hashing that block until they find like a special number. So they increment a certain number, they hash the block, and then the hash of the block needs to start with a certain number of zeros. If it starts with enough zeros, then the protocol says it's a valid block. If it doesn't start with enough zeros, then the block is invalid. And of course, finding the input that creates this very special hash with a lot of leading zeros is extremely difficult. It takes a lot of time, right? Now, This is actually done on purpose. It's purposefully hard to create a new block. And the reason for that is to create a kind of time delay where you want the next block only to be created a certain amount of time in the future, not too fast. Because if it happens too fast, then the chance that you will have these two parties finding a block at roughly the same time and then broadcasting it both at roughly the same time, you always get these sort of ambiguous moments where the whole network is confused about, hey, wait a moment, which is now the next block? So you want these time periods to be rather long. In fact, in Bitcoin, it's extremely long. It's 10 minutes, right? On average, 10 minutes between every block. So the proof of work acts as a kind of clock. It acts as a kind of physical time delay to space out these blocks and avoid having these forks. Okay. So this I already mentioned. In the block there is a kind of what's called a nonce, number only used once, and the miners, what they do is they just increment that number very quickly, always hash the block, and then check if it starts with the leading number of zeros. And that leading number of zeros that you have to hit, this is called the difficulty. And that difficulty is also adjusted, because the more compute power that you throw at the problem, of course, the quicker you will find you will find the solution, right? And in fact, so here's a graph that shows you on a logarithmic axis, by the way, where the blue curve is the total amount of hash power in, what is it, terahashes per second, right? So from virtually nothing in 2009 to about 1 billion terahashes per second. The black, by the way, just for reference, is the price of Bitcoin. And you can kind of see there's a pretty clear correlation between the price of the asset and the amount of compute power that's being used to secure it. Okay, but this is staggering because we're talking 1, 2, 3, 4, 5, 6, 7, 8 orders of magnitude change in hash power from Bitcoin's conception till today, and that protocol hasn't changed. It's still the same protocol. So what it's doing is every, 48 blocks or so, it looks at how fast did the miners find the blocks in the last epoch, and if that was too fast, we'll increase the difficulty. If that was on average too slower than 10 minutes, we will make it easier. So there's this difficulty adjustment mechanism. And that's brilliant because it actually allowed Bitcoin to survive 8 orders of magnitude of growth in the amount of compute power. Why was there so much growth? Well, of course, there's this just the network effect of Bitcoin becoming more known and, of course, more valuable, making it even more known, etc., etc. The other thing that happened is that in the early days, Bitcoin was mined on a regular computer, and you could easily find a block with enough leading zeros by letting your machine crunch for a few minutes. But then people used GPU cards, and then later people used FPGAs, and then finally people started creating special purpose ASIC chips, and so that today mining Bitcoin is an industrial thing. Like people have entire data centers filled with these machines to solve that hash puzzle, which is problematic because actually the original idea of Bitcoin was everybody can participate, and that is certainly no longer the case today. So there is a heavy centralization in the amount of mining power that happened over the years. Okay, I'm wary of the time, so I'm gonna skip over some content here. Well, yeah, this is actually what I just described. So this is a mining rig from, I guess, somewhere in 2012 or something, when somebody was just taking GPUs and then mining Bitcoin at home. And this is a ASIC-based mining farm, Bitcoin mining farm. And the reason, of course, that these parties win is because of economies of scale. So that's illustrated here. Economies of scale means that, the more production you put to use, the more efficient you will be, right? And so they're in terms of efficiency, they're driving the small miners out of business. Question. yeah, that is absolutely a concern. And to add insult to injury, there is not just the centralization of mining power, but miners will also band together in what are called mining pools. And that creates an additional level of centralization. And I do believe the biggest mining pools in Bitcoin are somewhere around 20 to 30%. So there is a heavy centralization. Now, of course, and this is one thing to keep in mind, let's say I hit 51% as a miner. Will I immediately start attacking the network? Well, what will happen to the price of the token? It will crash. But I have just invested massive amount of mining power in securing this network, right? So there are sort of interesting arguments of why this might not be an actual problem in practice. But of course, as I told you before, the security of a blockchain is really proportional to the level of decentralization of the scarce resource that is used to protect it. Okay. All right. Very briefly, so proof of work was the original consensus protocol used by Bitcoin. It has since been cloned by many, many other blockchains. Ethereum in 2022, I believe, switched from proof of work to proof of stake, and that's the other very popular algorithm. The big benefit of proof of stake is that it doesn't burn energy, right? So it's more energy neutral. And so the idea is that you lock up certain crypto tokens in some kind of deposit contract. And the more tokens you lock up, the higher the chance that you will win the lottery and propose the next block. And if you're caught misbehaving, then they can take that collateral that you deposited, the network can take that collateral that you deposited and sort of seize it and redistribute it to the network. So it creates a kind of economic incentive to stay honest, because if they catch you doing wrong things, like for instance, saying that you produce two blocks at the same block height or at the same index, if anybody catches you doing that, it's easy to verify that because you have to put your signature on it. They can actually steal your tokens. So it's a very effective way, but it could only be bootstrapped once people actually understood what a cryptocurrency was. And so that's why I think it was not the first system to be used, but very popular today. I'm going to skip over the details of Ethereum's proof of stake, but you can look at it later in the slides if you want to. Maybe a final thing, maybe you've heard of the blockchain trilemma. So this is a big, sort of a big focus point of how to build a secure blockchain, is that it turns out that there are these three dimensions to blockchains that are very difficult to combine together, which is security, which means, okay, how easy is it to protect against censorship, and also how easy is it to prevent these forks and to prevent these double spending attacks. There's decentralization, which you can think of as geographic decentralization, meaning the nodes are in different parts of the world. And also, they don't need to have like high-speed internet connection. They can be like small computers on slow internet links. And the more that is the case, the more decentralized the network is. And then there's scalability. And again, scalability you can think of as, do you mean the size of the network, or do you mean the amount of transactions you can push through the system? And one very, very clear sort of trade-off, so the red lines indicate that these things are each other's opposite. If you try to optimize for one, you will lose on the other, is between decentralization and scalability. So the more decentralized the network, the more nodes that are spread over the world on slow internet links, of course, the more time it will take to distribute all these transactions and get all the parties to agree on what is the correct blockchain. And so it means you will get a very poor transaction throughput. And indeed, if you think of Bitcoin, it has about 7 transactions per second. If you compute it, 7 transactions per second. Ethereum, I don't know, it was more like maybe 100 transactions per second. So they have like the incomparable transaction processing rates compared to traditional payment networks. Think of PayPal, think of MasterCard, right? That you can have much higher scalability. But of course, those networks are completely centralized, and here you have this decentralization. Okay. In reality, it's not really a binary choice. It's more like a spectrum, and you can engineer your blockchain on a spectrum between, okay, how scalable do I want it to be versus how decentralized? The other key point in the design space is these enterprise blockchains, which are typically like only 5 or 10 parties, like 10 big banks that come together. Yeah, those 10 big banks are not going to put their blockchain nodes on a slow home network. They're going to put them in a cloud data center. So these 10 blockchain nodes will talk to each other over high-speed optic links, and so they can easily do 100,000 transactions per second on a blockchain. Okay, so there do exist blockchains that can process hundreds of thousands transactions per second. They're just not as decentralized as, say, a Bitcoin or an Ethereum. Okay, so here's actually a table that lists for permissionless versus permissioned, like all the different trade-offs. But I don't have the time to go through them, so I will skip over that. I didn't get a chance to talk about Ethereum, but the key thing about Ethereum is that it makes blockchains programmable. So you can now upload code to the blockchain, smart contracts as they're called, and use those for getting like interesting, for doing interesting things like creating decentralized loans, prediction markets, lotteries, bidding platforms, like all kinds of financial constructions. But let me skip over that and maybe end with one final thing, which is some additional challenges beyond the introduction. So Bitcoin today, it was invented in 2008, is a fairly stable and well-known technology, but there's still a lot of open issues with the technology. For instance, privacy. The blockchain, everything is public. I mentioned it, there's no encryption. So you can't store secrets on a blockchain, so how do you do private payments? There do exist solutions. So you've heard of, I believe, zero-knowledge proofs this morning. So here's one application of zero-knowledge proof. There's blockchains like Zcash, for instance, that use zero-knowledge proof to do anonymous payments on the blockchain. Scalability issues, I mentioned it, right? So blockchains are slow, and one solution is these layer 2 systems that build on top of blockchains and allow you to batch together many small transactions into one big blockchain transaction. So you kind of 10x or 100x the transaction throughput, and this is happening on Ethereum with protocols like Arbitrum, Optimism, etc. Security vulnerabilities in smart contracts are a big topic. Then the problem of mobile clients or web clients. So if you use your home computer to look up your data on the blockchain, or use your mobile phone to make a payment with Bitcoin, the problem is that your phone doesn't track the blockchain. It can't download all those blocks, do all the transaction processing. So you typically trust a middleman. You trust some server to relay your transaction to the blockchain or to read data from the blockchain. And there's also my group also does research on how can we get rid of those middlemen? How can we let the clients talk directly to the blockchain without any loss of trust? Interoperability. So Bitcoin started with one blockchain, then the idea got like copied over and over again. Today there are hundreds of blockchains, and now the problem becomes, how do I transfer assets that are stored on this blockchain to somebody who has an account on this other blockchain? So you need to like make these blockchains interoperate. And that's an interesting problem. And then maybe finally, as the very last thing, and it was mentioned in the last presentation as well, post-quantum, right? So quantum computers will be able to break elliptic curve cryptography using Shor's algorithm. And so we need to transition to post-quantum signature schemes in order to make these systems like Bitcoin and Ethereum quantum secure, post-quantum secure. And these are, of course, discussions that are actively going on in that community. All right, that was it. I hope you found this interesting. If you have any further questions, I'll stick around for a few minutes, and thanks so much for your attention.